Hello, everyone. I think today we have my opinion, the most exciting part of the presentation because it's more like hands-on and practical. So I call it the LLM Scientist Toolkit, or this is the part that made me believe that the language model scientist is coming up as a new profession. So today I'm going to do something I haven't done the other days. We're going to go through some presentations, and then we'll switch to a different deck and show you a particular one from the beginning to the end, just because I think it was interesting and I think you're going to like it. So if you remember when we discussed data monetization and scaling laws, we talked about, we know the traditional scaling law that it's a power law showing that you throw more data, more compute, you're getting better accuracy. But then if you remember, there were cases where if you do a better selection of the data, you can actually scale even better. You can get even better performance. So I consider this as a really interesting invited talk. It was from, again, coming from the Atrib workshop. We've talked about this a lot, where scientists in general, researchers, try to see, is there a better way to select my data? And can I actually train the same model in less data? And that's kind of like the message here. I have the link over here. It was an ICML 24 tutorial on foundations of data efficient machine learning, which you can skim through. But the idea is that smaller subset of big data yield better performance, and of course you save compute. And this is the case of CLIP. So for those of you who don't know, CLIP is one of the state-of-the-art algorithms for image labeling. And this is the CLIP zero shot performance. This is from Datacomp 23. I don't know if it's the same paper Datacomp that we saw this year. Anyway, you see that I think in let me see if I remember here. Smaller high quality, yes, smaller high quality data, yes. So the smaller high quality data can offer higher efficiency, and I think they have that. They show with 40% of less data, you can actually get the same performance, or the same way, with less data. In total, you can get better performance. Yes, now I remember that. Sorry, I just switched from another meeting. There is a big gain when you even select less data. And I think this is okay. Now I remember, this is the original CLIP paper where you use less data. By just randomly selecting 62% of the data, you're getting less performance. But it goes the other way around on the Lion, where they do a better selection of the data. Sorry? Sorry, we got some noise. And this is, another case on Pythia, 440 million versus 1 billion. And you see that 50% subset performs the full data. And I'm not going to go against the technical details. They're based on something called core sets, which we've seen before in other parts of machine learning. The idea, can we find mini batches that guarantee superior convergence? And you can see here some really exciting results. The method is called COLM, course sets on training language models. So I find it odd because finding course sets is not an easy task, but apparently they did a pretty good job over here. And it says Colm outperforms normal fine-tuning for 1,000 iteration with batch size 128 and 1,000 iterations with batch size 256, while being 1.3 and 2.7 times faster respectively because they're choosing less data. And here, what is interesting is they even do it for pre-training, because pre-training is a very hungry process. And I want to go back to what I said the first day. We thought that this is a task for the big guns. Obviously, DeepSeek kind of like shook the community. But I think if you had been at NeurIPS, you would have seen that with rigorous science and good research, you can still do more with less. We've seen that as a trend everywhere. And here are the references. Now we're shifting gears. This is another tool, which to me, it's kind of interesting that everybody's looking at reinforcement learning because of DeepSeek, but it was already there, and don't forget that these are papers that were submitted almost a year ago, 8-9 months ago. And this is a framework. It's an open source framework for doing reinforcement learning. They have a big spectrum of methods, and they support Megatron and VLLM. Again, an extremely useful tool. So now that thanks to DeepSeek, people have shifted their attention to reinforcement learning. Here's a great tool that you can use, and they actually show you how it fits on the whole training stack. And here they summarize the components. They have multi-controller engines. The controller, I think, here is the policy. So they have the actor model, the critic model. They implement a really wide variety. I don't really think people need all of them, but it's good to have them. And it's nice that they have been implemented in different frameworks. And this is also another package. Actually, no. I think it's the same package. I'm sorry, not the best of my days. I think it's a different package here using. Yes, if I can. No, actually, it's the same package. So we can use existing reinforcement learning for LLMs, and the answer is yes. And there's probably, again, I'm not an expert in reinforcement learning, but I know the gene, but I'm not familiar with RLib and Runner. So apparently they're integrating with them as well. Now, let's go to an expo talk. Again, for those who don't know, expos are talks from the industry. And I can't remember which company is talking here, but this is about mastering distributed training, best practices for scalable model training. And here's the distributed training landscape. I mean, again, in the past, we thought that we'd never use it, but there's been a lot of research. I'm particularly familiar with HPC AI, the Colossal AI, basically. They actually have a nice framework. They're the guys that they did the Open Sora. And there's different levels of parallelism, 3D, 2D, and in this particular, okay, it was from Lambda, now I remember that. So Lambda Labs has this expo talk. Looking ahead, 4D parallelism, data parallel, tensor parallel, pipeline parallel, and context parallel. I haven't used their framework, and I haven't really been in that business, but it seems to me that it's available. It's not completely out of cost. Then another tool that the modern language model scientists to have is a way of benchmarking, agents. We know most of the applications are based on agents. And surprisingly, this is, not surprisingly, it's not an easy task. so that's kind of idea about how the LLM powers agents are working. We've seen that before. We presented that paper in a previous section. So if you want to hear more or learn more about that, you can go to I think it was the second day of NeurIPS, where we talked about agents. Now, this particular expo from AWS was one of the ones that I really enjoyed. So it talks about the MegaBeam Mistral 7B and how they build a very long context language model. From our experience so far, it seems to be working really well, and we were quite impressed with it. So it has a window, an impressive window of 500,000. And the goal was to be lean and capable, to handle obviously 500,000 tokens, retain short context capacity. It's licensed under Apache 2.0. And the ruler is a long context benchmark that, has to do with retrieval, multi-hop tracing, aggregation, and question answering. You can read more about it in the reference. And you can see that MegaBeam performs really, really well compared to other models that are much bigger and expensive in both benchmarks. So here it's second, here it's fourth, but not really very, very far away from the state of the art. And this was like a use case that they took transcripts and logs where more than 300,000 tokens, and they loaded in the context, and then I think 15,000 tokens is the output. They're trying to do some tasks. They had to do matching, classification, and reasoning. I think another use case that they particularly like is there is a command which you can export the whole GitHub repo as a text file. I think they have it in the presentation. I don't remember, but GitHub offers that capability. And then they load it in the context, and you start asking questions. So it's a really good tool if you want to, as a coding assistant, not a copilot, but trying to find where things are and asking questions and answers. And they also used it for, it says Houston, we had a problem. They needed to run some iterations, so they have a use case. Unfortunately, the screenshot didn't come. I need to retake it. You can go to the presentation and find it. They used the Mistral, the MegaBeam, and they were able to, I think I know what was the problem. They were, you're getting an error, you put the compiler, you correct it, you put again. So you run iterations, you keep refactoring the code based on the compiler feedback. There is a bunch of applications on the left, and they take some kind of history. So Falcon Light in 23 was 12,000. Then again, August 23, 24. Mistral Light, September 23, 32. Then they won MegaBeam. The first one in August was 32K, and August 24, they went to 512K. They talk a lot about how they did it. I think it's worth reading the paper. There are some interesting applications. So they list them over here, but I just wanted to point a little bit the performance. One of the problems is that when you increase the context, slows down training or it stops. And they have an example over here that they kind of show that how they can achieve more teraflops when they compare to GPT-3. These are the small GPT-3s, of course, okay, not the big ones. And they hit some out of memories, but they did their engineering right, and they were able to maintain the flops they needed. Now, in a sense, if you have a long context window, you can also create or process an image, a vision transformer, multimodal, because it says the average length of, okay, so an image 336 by 336 into 14 by 14 patches, it's 576 tokens. It says the average length of a YouTube video is 11.7 minutes. So basically, you could fit a whole YouTube video into MegaBeam, and who knows what we can do with that. You know, one of the sensitive part is how do you increase the context, and it has to do with generalization by scaling rotary position embeddings. I'm not, you know, I know how rotary embeddings working, but I don't know what was the key that they did over here. But if you're interested, you can look more. And again, that's in our presentation. You can find more stuff over there. Okay, now another interesting talk from our team. Again, we're going into this motif. Teams are doing the same task again and again, and sometimes they come up with theoretical knowledge, like the core sets we saw, and in some cases they come with just like some practical rules, which are also very helpful. And let's see some quotes over here. This is from Neptune AI. Challenge: hardware failures. Rule of thumb number one. Rule of thumb: one failure every 1,000 GPU days. This is a statistic from someone from Databricks. Another one: when training LLMs, I think this is very interesting. There is pain from all over the place. The lowest level source of pain is you get a ton of hardware failures. And when you get a hardware failure, it does not raise a hardware failure exception that you can catch and handle. Maybe your job completely crashes. Maybe some of your nodes slow a bit. You can even start getting suddenly incorrect outputs. I remember the Gemini team talked about that at NeurIPS last year. And now it's up to you to figure out what it is. So that's really interesting because, you know, one of the biggest assumptions when you write software is that, you know, the processor executes what you tell it and does not start giving you errors, numerical errors. I mean, this is a hardware error. It doesn't do the addition properly. It's not like an overflow or something like that. You know, it's the same thing at a different stage. It would have given you the correct, and now it's giving you something else. Another challenge, managing and visualizing data, is our ML team at Wabi continuously ran large-scale experiments with ML models. A significant challenge we faced was keeping track of the data they collected from experiments and exporting it in an organized and shareable way. I mean, who would imagine? You know, data management is a big thing. Single source of truth. We trained more than 120,000 models in total for more than 7,000 subproblems identified by various combinations of features. We stored a lot of metadata, visualizations of hyperparameter tuning, predictions, pickle models, etc. So how do you manage all that stuff? And of course, people want to visualize. I needed to extract about 1 billion tokens from a very large data set, but I didn't know ways to visualize, to understand what is the relationship of all those tokens. I don't know of any good experiment tracker that would take on that volume and display that text data in a proper way that I could be able to understand the embeddings. We kind of saw, we've seen a tool before, and I don't remember which day it was, about managing and visualizing pre-training data. I think it was called Big ML or something like that. Now, this is something we're going to see later on as well, the spiky loss curves, that they can be attributed to several problems. One of them is, you know, bad batches and bad data. And there's a nice, I believe it's a paper, I'm not sure if it's a blog post from Databricks, training LLMs, lessons from the trenches. Again, another nice, interesting source. We need, and we are building more tools for training at such a large scale. The software stacks are not mature. There are breaking changes in NVIDIA, PyTorch, Hugging Face libraries. Whatever abstraction layer you're using on top of those will experience breaking changes. Everything is unstable, and you spend a lot of time building some kind of layer to abstract it away. You're checking for different torch version numbers in your Python code and monkey patching different functions. Interesting talk from Mosaic. We identified the lack of tooling as soon as we started planning and building consistent benchmarking as benchmark data sets. We considered our workflow and recognized that sharing benchmark results in a constant place and format and retaining data for later comparison after the end was critical. You know, obviously reproducibility and transparency is another thing. And, you know, again, it's an interesting talk to just get an idea about where we are. It's not a rose garden, but we're getting there. Eureka, another evaluation framework for understanding large foundational models. We talked about agent board before. This is a little bit different. This is from Microsoft. Here's the paper. And, you know, I'll just jump to the end. Challenges and differentiators, saturated benchmarks, challenging benchmarks, development challenges, evaluation of general capabilities, transparency, reproducibility. We talked a little bit of that. There's a lot of variance. You know, about the multimodal models, they say that the state-of-the-art multimodal models struggle with detailed image understanding via high-level understanding. Kind of like started this presentation, this series with that DALI image, trying to explain that although that was image generation, wasn't multimodal. You know, I've seen that in practice, multimodal capabilities, language capabilities, and complementary performance across models for fundamental multimodal skills. It's there. This is very interesting about non-determinism. And we see they categorize the models into highly non-deterministic. This was the beginning of GPT-4 and Gemini. Then there was low as Llama came, and then GPT-4o and Claude seem to be, they're still notably not deterministic in highly generative tasks, but they are the next most deterministic models, but not zero. Okay, so you can go and see the leaderboard, and here's kind of like a summary. We've seen this before when we talked about agents, the AutoGen 0.4, which is the Microsoft agent stack. I think it's gaining some traction. It's an interesting framework. We've used it. And it's basically, I don't want to get into details, but that's kind of like an interesting demo where you build an assistant agent. And this is kind of like your logic. You know, the reason models, he gets a response. If the response is an action, then you execute that. You execute that action. You take the observation, and then you reason over the observation, and you get the response, and then you get the output. And then it gives you an example like find a time on Friday to book a meeting with Eric. The reasoning is I need to find available time slots, and that leads to the action. You know, what's the available time slots, observation, and going on. And you can build quite complicated workflows. You know, this is about the life cycle of a bug, and you can have different agents. Again, you can even build a whole company, like the Magentic One team. You can go through the you know, the website and the paper, and you can read that. And they have, I think, I'm not sure if that's something they already have, but they're aspiring to do. Low, no code, visual experience, drag and drop, high level concepts, and powerful building blocks, and opinionated scalable systems. Again, something to grok. This one, active training, building agentic apps with Llama 3.2 and Llama Stack. That was like a long workshop. They have, this is the agenda. We don't really have time to go through everything, but this is what you're going to find out. Llama model evolution. What does it take to train llamas? What can you do with llamas? and introduction to the Llama stack. And then they spend some time doing hands-on. The reason why I haven't put it is there's a lot of hands-on exercises on that. Yeah, I just can give you one slide over here. The anatomy of pre-training. These are some steps that they took. Data mix adjustments, long context speed pre-training, and annealing. These are the 4 components, but you can find more of the presentation. Now, you know, the AI, Allen AI have their own stack, and this is a tutorial. I think it's about 250 slides. You can have the slides here of the, and of course you can watch the video. What I'm going to do is I'm going to jump I'm going to go through the whole presentation for this one very quickly because I think it's interesting. Just wanted to make a note over here is that Allen AI is actually it doesn't have the credit it deserves, because everything started with Elmo, which didn't have transformer. It was based on LSTM, and that's why, you know, cartoon wise Google responded with BERT, and then OpenAI of course used that technology, half of that technology, and moved into GPT. But I think they just wanted to highlight that you know, they kind of like started this track, and you know, the idea is that we provide all the everything you need in order to run, in order to build the language model from start. So this is the agenda, and we're not going to go through that because this is too big, but they give another invited talk, which is a smaller version of this one. And this is the one that I'm intending to go through. This talks about Olmo and Molmo. And these are the references. And I'm going to show you a trick. If you go to my presentation, there is a hidden slide in the beginning of every section. We go here, 288. Okay, it's this one. And this one basically has all the agenda. And if you click on that, it takes you to another presentation that has the raw slides. Okay, so I'm just going to go through that because I like it. And again, we saw the references. We need language models that they are fully open. And here they go through, you know, what has been so far. And probably only Bloom checks all the boxes of what is transparent and really open source. Now Olmo offers everything. It's truly open. And again, just for the stack, they give you Olmo, Olmo 2, Olmo, mix experts of Olmo, and I think Dolma is the data set, the pre-trained data set that they have created. And then they have the multimodal, Molmo, and Pixmo. Pixmo is the vision transformer, generative vision. Yes, I think it's a transformer. And then they give you a data set, Tulu and Olmo Instruct and OpenInstruct Toolkit. So they give you instructions and more about how to do the post-training. So you got everything. Design principles, fully open, scientific, high quality, and efficient. And the post-training is actually very useful and interesting. Olmo, the first version was better than Llama 2. Olmo 2 is now on par with Llama 3. It's not exactly there, but they're working on it. Mixer of Olmos is best in class, according to them. Go a little bit quickly. You know, this is their vision language model. And they give you some statistics about the different models and how it was trained. And here is the Tulu 3, which is, again, the next generation of open post training. Probably has a lot of instruction sets. Olmo 2, 7 billion, 13 billion was trained on 5 trillion tokens. You can get access to that. Pre-training runs are costly. You can see here how it grows exponentially. to almost 500,000. Do more with less compute, optimize quality versus cost. So before the pre-training run, you do some experiments with smaller models to see how you scale. And during the pre-training run, you're trying to remove spikes and improve training pipelines. So before the pre-training run, train small LLMs with curated data, evaluate in selected benchmarks, and see how it scales. Okay. So you take decisions about database. So that helps you your configuration. And then you have to build a predictive model that predicts the model at the larger scale. So you have to see where you're going. Okay, so I'm just kind of like giving you the recipe a little bit quickly over here. And then again, during the pre-training, remove spikes, because a mistake in pre-training can cost up to millions of dollars. So you just don't press a button and you let it run. You have to babysit it. And that's kind of like an example where things show that your training loss is doing well, but apparently for this, I don't know what kind of run this blue curve on the downstream tasks, you get horrible performance because something is going wrong. And you have what the people call the fast spikes. And now you wonder what this microwave is. Apparently, it's bad data. So this just happens that was from Reddit, where you have like this awful bad data that they have to do something with microwaves. And welcome to the microwave gang, where we talk about topics as okay. And you remove them, you get more stability. You can have increased context length, because again, context length. Although you don't do this, it says more in the presentation how you increase your token, your context length. You don't do it from the beginning. So anyway, these are lessons that they've learned. And now the new Olmo is on par with Llama 3, Olmo 2, the specific edition, 1024. Okay, we've seen that. Okay, why mixer of experts? As you can see, mixer of experts give you better training loss, validation loss, and the biggest thing is that there's 3 times less flops or tokens, and especially when you are doing inference, this much smaller portion of your network is active. And the idea is really simple. This is the layer that it's costly, the feed-forward network, and you kind of like put a router that activates some smaller experts each time. And it doesn't seem that complicated, but apparently, if you swap in the mixer of expert train as is, you get horrible performance. And there's some, some improvements you have to do where they kind of like list them over here, and you get better results. And you can see now the training looks much better. And here they show some benchmarks, and because you have less tokens active, you can put it on an edge device. It requires less computation. Okay, so for the Molmo, I think what it's really interesting is it says you start with off-the-shelf large language model and visual encoder, but same release, they had the same release day. It says Molmo model outperformed Llama 3.2 in most vision benchmarks. And here's what the key was here. The key was here in the data selection. So Llama 3.1 has 6 billion image text pairs, and they only have 700,000 image text pairs, the Pixel. So here's kind of like an interesting thing. Now, you have a photograph, and look at this nice description that they have. Very informative. Okay, you won't find in this training data set, because I think they use something that was that other people have done before. And I think it was quite clever, because these guys thought about it and said, how can we accelerate the annotation process so that we can create high quality training data? And they did a simple trick, simple hack. Humans don't like to type as much as they like to speak. we ask annotators to speak for 60 to 90 seconds about an image. And then they use language models to convert the formats that they needed, to transcribe that. And, they did it even for images like that, point to menu, point to where I can set search options. So, oh, sorry, this is a different one where they're collecting data where, you basically, you have the instruction and you have the pointer. That was also interesting. I don't think the others had that. There was basically, navigation, clickstream in a sense, data they generated. And they gave them tasks like count the boats. They created more tasks. Pointing examples, we talked about, count the cars on the right lane, cars on the left lane. And they created a better training data set. And okay, we're getting closer to the end. Tulu, let's go to Tulu post-training. LM adaptation. The raw pre-training LMs are neither safe nor robust for public use and interactions, thus require alignment between AI and humans. If you were one of the first users of GPT 3.5 before ChatGPT, what you had was basically a pre-trained model, and you would remember how bad it was. And instruction tuning came, and they have a list of basically different skills that they created data sets, and they made them available and at a lower cost. Okay, sorry, we stop here. That's a different thing. All right. We have a few more minutes to finish the presentation. I hope you find that interesting. We rushed it a little bit, but I feel like it was worth it. And we are here. Okay. I think I'm not sure if we've mentioned that in a different part of the talks, but this is the linearity of language models. Now, this is something that, in my opinion, it's very important, and I'm not sure it was highlighted enough. It came with the title, "Why has predicting downstream capabilities of frontier AI models with scale remained elusive?" Okay, you might remember in the Word2Vec that there was a vector that could take you from France to Paris, from China to Beijing. So there was like this linearity between embeddings. Okay, you could do basically reasoning by addition and subtraction. The queen is man minus woman plus king, and all that stuff. But if you remember, people analyzed and said, well, that's interesting, but it doesn't really work, for all the concepts in Word2Vec. And it turns out it doesn't work for all the concepts in language models. And the question is, why do linear features form for some concepts and not for others? And, again, that was linearity is not always given. And they did some analysis over here. And long story short, it really has to do with how many times you've seen it in your training data. Like this is an old paper. This is from 2001, where actually Hinton and Pacanaro had observed this thing. But it turns out that you still need to do some pre-processing to your data and make sure that you have enough co-occurrences of the relations that you want to maintain. But I feel like we're going to see more over there, because remember, we're going to see that tomorrow when we talk about language models merging. I think it's tomorrow's talk, where we need to add language models and combine them. That linear property is important to have. So it works well when this is there. So I believe in the future we're going to see more papers to guarantee that property. Evaluating and forcing linearity. Okay, so this is, I think I kind of rested because we ran out of time. How many presents are linearly in a model? Like almost 7 billion. They spent some time, they analyzed, and they actually found in every data in Oldmo, for how many relations this linearity is preserved. Okay, when attention sync emerged in language model, this is something that I wasn't aware of, but apparently it's a big problem. It's called attention sync. Maybe most of you haven't heard of that before, but this is the idea where attention sync refers to that language models assign significant attention to the first token, and that in some cases, leads to collapse. And they talk about what we can do with attention sync, and there are some kind of like recipes over here. It's not it's okay. You can read more about it. And I think we're almost done. Evaluating large language model principles, approaches, and applications. I don't think we have time to go through all of it. Let me see how many slides we have. Okay, we can go through that. So this is the Gen AI app lifecycle. How to craft the prompt template. Is the model a good fit for the use case? How to augment the model's knowledge? Can tuning help? Is the model performing over time? Launch. And this is what they talk about: the task-specific evaluation, use case, data representing your application, context. Model is one of the Lego bricks, criteria, your definition of success. It's more like a model management. And these are some results from the battlefield. Automatic evaluation is the holy grail, but still a work in progress. Without it, engineers are left with eyeballing results and testing on a limited set. So basically, in short, this is like, how do we do CI/CD for language model applications? And they have Autorator, which is a system, again, another tool that emerges. So, here you can read more about like prompt formatter and fixing and maintaining. This is more like a DevOps tool for language models. And now here they also have a bunch of benchmarks. Maybe we can go through the summary. 3 approaches to LLM evaluation: computation, human, Autorator. Support your application and task. Choose, customize, calibrate. Okay, just last one. This is a paper that I really like. Panoramic view of representations. It's basically a way, you might remember when data science, when data science became popular, you did topic modeling and you were getting the word clouds, okay? And the word clouds will show different words, and it was a nice visualization. Apparently now what you can do with this Vista is you can do clustering, and you cluster, let's say, your images, and that goes through it's the new Disney, as I call it, because let's say that you have a cluster that represents, I don't know, these warriors over here, and it goes through a Gen AI tool and it visualizes, it generates images, like it's a new visualization of your clusters with I think it's diffusion here that is that they're using. And they have some really, so basically this is a visualization of a data set based on clustering. So it clusters things together and creates a visualization. I think it works either with text or with images. No matter what data you have, it can interpret that. That's also another tool. It's like an in-painting, where you in-paint something and you say, well, put a mouse, you have this image and you say, put books and a mouse on top. And I'm going to stop here. Thanks, everyone. We're a little bit out of time today, but pay attention to that last library. I think it's really impressive to present your results like that.